These are your notes for graphing parabolas or quadratics. It's going to follow the notes in Glencoe 6.1 and 6.6. Looking at our first example, we're given a function f of x is equal to 2x squared minus 8x plus 9. And another way of saying this is just y equals 2x squared minus 8x plus 9. Okay? A few things to notice, a few observations, is the fact that we are in standard form. And our constant c is going to be our y-intercept, or where we cross the y-axis. The reason is because y-intercepts have x values of 0. And if you were to plug in an x value of 0 into both of these terms, those terms would disappear, okay? So if we're making a table of values, that's actually a good place, or a good value to always include your y-intercept. Now in the book, I'm going to get a little bit ahead of myself. I'm going to find the axis of symmetry. And I kind of like to refer to this as my midpoint of my parabola. And the equation to find it, if you recall, is negative b over 2a. My b value here is negative 8, so negative times negative 8, all over 2 times my a value of 2. So we have 8 over 4, which means our middle value, our axis of symmetry, is at 2. Now the axis of symmetry is also the location of our vertex, okay? But to find the y-coordinate of my vertex, I must plug in my x value of 2. So I'm going to plug this into my equation here. Make sure when you are plugging this in that you are following order of operations. And what I mean by that is, first we're going to square the 2, then we're going to multiply it by 2. So 2 squared is 4, and 2 times 4 is 8. Minus 16 and a plus 9, and we get that we're going to have a y-coordinate of 1. Now the special property about axes of symmetry is coordinates that are equidistant away from our axis of symmetry are actually going to have the same y-coordinate. So notice that 0 is 2 units away to the left from our axis of symmetry, so it's going to share a y-coordinate with 4, who is also 2 units away from our axis of symmetry. Okay? Notice that we're going to miss between 1 and 3. They are both 1 unit away from our axis of symmetry. And I can plug in either one, and they're going to have the same y-coordinate. So let's plug in 1 because it'll be a lot easier on ourselves. So once again, work smarter, not harder. 1 squared is 1, and 2 times 1 is 2, minus 8, and a plus 9, and we get a y-coordinate of 3. Now all I need to do is plot my points. Alright, sorry about that. Sonny was going a little bit crazy here. Must be a dog in his yard, and it's not really his yard. Alright, so let's plot these coordinates. So our axis of symmetry was located at 2, 1, so there's my point right there. And then we also had coordinates at 1, 3, as well as 3, 3. And I'm going to start to go off my paper here, and I'm going to start connecting my dots, okay? A few observations, a few concepts that you should still recognize is the concept of domain and range. Domain are all the possible x values that you're able to plug into your parabola. So notice that I can plug any values to the left and to the right of my parabola. They're all going to work, so my domain is all real numbers. Now my range are all the possible y values, and notice that I don't have any coordinates down here. In fact, the lowest y value I ever get to is a y value of 1. So we are y is greater than or equal to positive 1. All right, let's take a look at example 2. Once again, we are given a parabola. In part A, we're supposed to identify 3 different things. The first thing we need to identify is our y-intercept. So it might help if we actually rewrite our equation in descending degrees. So x squared plus 8x plus 9. So now I can clearly see that my y-intercept is positive 9. So I can just show my coordinate for a y-intercept of 0, 9. Now the equation for the axis of symmetry is negative b over 2a. My b value here is 8. So we have negative 8 over 2 times my a value of 1, which is going to get me a axis of symmetry of negative 4. Now the axis of symmetry is actually an equation of an invisible line that we reflect across. So here is my equation for my axis of symmetry because it's the x-coordinates that are symmetric to one another about this point. Now that also means that the x-coordinate of my vertex is also negative 4. So now let's make an XY table, and just like the textbook recommends, I always put the vertex smack dab in the middle because then I know points on either side of him are going to be symmetrical. So for example, -3 and -5 will have the same y coordinate because they are both one distant away from the x value, my axis of symmetry. So just like that, we have -2 and -6. Both of them are going to have the same y coordinate. So if we take turns, we plug things in. So we have -4 squared plus 8 times -4 plus 9. Type that in very, very carefully, and you get a y coordinate of -7. I'm going to plug in the smaller values. Work smarter, not harder. So we have -3 being plugged in. And when we type all that together, we're going to get -6. And then lastly, let's also plug in -2 into our equation for our quadratic. And when we plug in -2, we get a y value of -3. Okay? So now we can we can precisely plot the points on our parabola. So -4, -7. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So he's kind of actually off of our graph, and that's okay. So then -3, -6 is going to be approximately right here. Am I counting these right? 1, 2, 3, 4, 5, 6. Oh no, I'm not. Erase that. So each block, 1, 2, 3, 4, 5, 6, 7. Oops, my apologies. So -4, -7. There's our vertex. Here are two of our coordinates that both have the y value of -6. And then at -2, -3, here's our point right here. And then here's our parabola going upward here. And actually, it looks like we're going to cross the x-axis, so that means we're going to have two real intercepts, real solutions. I kind of drew a smiley face here. Let's extend this concept a little bit further. Once again, the domain here is going to be all real numbers because I can plug in any x value that I want. Now the range, even though it doesn't show it on my graph, I'm actually not anywhere down here. I can't be any of these y values. So I am bigger than or equal to -7. All right, let's continue on and let's work on our next example where we're just really identifying whether or not we have a minimum or a maximum value. And minimum or maximum values, I'm going to have a maximum value when a parabola opens down. And what a maximum value really is just hitting a high point and then going back downward. Whereas minimum value, that means I'm opening upward and I just hit a low point, kind of like camel humps. That's kind of the way I like to put it. And when I'm opening down, this means that I'm going to have a negative a value, and I'm opening upward if I have a leading coefficient or a positive a value. So in this problem here, I have x squared, and actually my a value is going to be a +1 here, which means that I'm going to be opening upward. Because I'm opening upward, that means I have a low point or a minimum value. Now, what is the minimum value? The minimum value is the lowest y value because it's actually a height component. So the lowest y value will be contained within the vertex. So one of the things we can do to find the vertex is first find the axis of symmetry. So my b value is -4, and I'm going to plug this into my equation here. So we get 4/2, which is a vertex or an x value of 2. But what is the y value? So we need to plug this into our equation for our parabola, and we get a y value of 5. So we have a minimum value of 5, and we can also recognize the fact that our range is going to be bigger than or equal to 5 because we are going to be growing. We're going to be going up, 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 up to positive infinity. All right, so here's the last example for 6-1, and it's a real-world example, so let's read it out loud together. 400 people came to last year's play at this high school. The ticket price was $5. This year, they're hoping to earn more money, and they estimate that for every 50 cents they increase in price, 10 fewer people will attend the play. So while it sounds like a linear programming problem, it's actually just going to be a quadratic, where the total amount of profit or the total amount of money we make is going to be equal to the number of tickets we sell. Okay, so number of tickets we sell multiplied by the cost per ticket, okay? Which makes sense. Number of tickets multiplied by the price per ticket, it's going to equal the total amount of profit. Now, what is X going to represent here in our scenario? So I was thinking about this and trying to figure out how to explain it, but notice that we are only increasing by 50 cents. We don't know how much we're actually increasing by. That's what we're trying to figure out. So X is actually going to represent the number of increases we're going to make, okay? So our total income, that's what I of X represents here. First off, what is the number of tickets? Well, they sold 400 last year, and then we're taking away. So they're saying we're going to lose 10 people per the number of price raises we have, and that's what this 10X represents. 10 people for every 50-cent increase, multiplied by the money per ticket. Now, last year it was $5 per ticket, but we're going to be adding on 50 cents and X, so 0.5X, because we don't know how many more increases we're going to be having. What if we increase by $1? That's when our X is equal to 2. So now we just need to multiply our expression here. So I'm going to give myself some room to multiply. And we're going to FOIL. So we're going to have 400 times 5, which is going to be 2,000. We're going to have 400 times 0.5x, which is going to get me 200x. We have negative 10x times 5, and that gets me negative 50x. And then we have negative 10x times 0.5x, which gets me negative 5x squared. Okay. So notice that I actually kind of combined my terms in vertical method. And I'm going to rewrite this so that I have it in descending degree. So we simplify this expression here. And we now have our equation. Okay, so now we need to figure out how many price increases we need to make. And remember, that's what X represents. And we're trying to maximize this. And we know it's going to be a maximum function because we have a negative leading coefficient, okay? Now, the absolute maximum will be our maximum value, which is going to be located at our axis of symmetry. So we're going to do negative b over 2a. So our b value here is 150. So we have negative 150 over 2 times negative 5. And then this expression is going to simplify to be positive 15. So we need 15 increases of 50 cents. Wow, what a big increase this drama club is about to start charging, okay? So think about it. They have $5 currently, and we are going to add 15 times that 50 cents to figure out how much they're charging. And that's going to bring our new total charge per ticket to being $12.50, okay? Now, notice that part B asked for me the maximum income. Now, income was our function of y, so we're just trying to figure out what is the y coordinate located at my vertex. So all I need to do is plug in my x value of 15 into my equation, showing all my work here, plus 2,000. Oop, that looks like 2008. Oopsies. And when I plug that in, I get a grand total of $3,125, all because they increased their total ticket cost by $7.50. All right, so now we're going to move into 6.6, where we're starting to analyze vertex form. And I have to say vertex form is possibly one of my most favorite forms of the equation because it tells us a whole lot of information. It tells us what our a value is. It tells us what our horizontal translation is and what our vertical translation is, which is helpful because we're always going to relate this to our parent function. And just as a reminder, our parent function is just y equals x squared. So if I quickly draw what y equals x squared looks like, here's the parent function of y equals x squared, just to give us a little bit of help when trying to figure out what this one actually is telling us. So we have this equation y equals x plus 2 squared plus 1. This tells me that I have a vertex located at, we really have x minus negative 2 here, and we have an a value of 1. So our vertex is actually located at negative 2, 1. So if all of a sudden we're relating and comparing it to our parent function, oops, There we go. Negative 2, 1 is located right here. Notice that the vertex for our parent function is at 0, 0. So in terms of transformations, we move to the left by 2 units and then up by 1 unit, which is evident just by looking at our equation here. Notice that the inside connected to the x tells us our horizontal transformation. We move to the left 2 units. On the outside is our value for k. He tells us how we shifted up. We went up 1 unit. Now our value for a1 is no transformation, but he would control our vertical stretch, okay? So now let's finish graphing our polynomial. We can also follow the same pattern here because our a value is 1. So something fun to notice is that for our first 2 points, we go up 1 over 1. So we have a coordinate here and a coordinate here for our parabola. Then notice from this point, we went over 1 and up 3. So if we go over 1 and up 3, we're going to have a coordinate here and here. So here, maybe it will help if I put it in a different color, is the equation of the one example 1. Another thing to recognize that vertex form helps us identify is our range. Because we can recognize what direction we open, we can recognize that our range, which is all possible y values, or y can't be anything below here. So y must be bigger than or equal to positive 1. Remember with our domain, because we can plug in any values for x, we have a domain of all real numbers. I'd like to point out that you have a chart to fill out on this page, so please make sure you are filling in the chart and put it in your own words because that'll be the most beneficial for you in your notes. All right, so I'm actually going to take a different approach from your textbook for this example too. But to put something in vertex form, there's many different methods, but one of the best ways is actually to complete the square, and this will be really helpful when we do our conics unit. All right, so first things first, I need to move my constant term onto the other side. So we have y plus 5 is equal to x squared plus 8x, okay? So now if you remember with completing the square, we need to balance our equation. We're going to add a perfect square onto both sides because this is going to create a perfect square trinomial. That's our goal. So we're going to take our b term, which is 8. We're going to cut him in half, and then we are going to square this. So 8 divided by 2 is 4, and 4 squared is 16. So I'm going to add 16 onto both sides. So we have y plus 21 is equal to, well, the perfect square factor here is going to be x plus 4, because remember, this is always going to be half of your value for b. So then last thing, we just need to subtract 21 onto the other side. So we have x plus 4, that quantity squared, minus 21. Once again, remember that just by looking at this, I can tell you that my coordinate for my vertex is at negative 4, negative 21. Another piece of information I know about this parabola is that it's going to open upwards because I have a leading a value of positive 1. Okay, so this vertex is going to be located at a minimum value. Another thing that I can tell you just by looking at this equation is the fact that our range is y is greater than or equal to negative 21. I want you to start to recognize how much information you can gather just by looking at an equation. Another piece of information is that I can tell you we are going to move to the left 4 units, and we moved down 21 units. Remember, these transformations are always in comparison to our parent function. All right, so once again, I'm going to take a different approach than the textbook. I'm going to complete the square by adding 1 to both sides first off here. Next thing I need to worry about is the fact that I have an a value that's not 1. So I'm actually going to divide everything by negative 3, which is going to be the same thing as me saying negative 1/3 of the quantity of y plus 1 is equal to, so over here we have x squared minus 2x, okay? It looks bad right now, but fear not, you're in good hands. All right, next thing, to complete the square, we are going to add a perfect square onto both sides. That'll help us complete it. Remember, the ultimate goal is to create that perfect square trinomial. So what's half of negative 2? Well, that's negative 1. And negative 1 squared is going to be positive 1. Notice how I was adding information into my perfect square trinomial while doing it, because that's always half my polynomial. Okay, so over here we have 1 plus negative 1/3 the quantity of y plus 1. So I'm actually going to subtract this one. So I have negative 1/3 of y plus 1 is equal to x minus 1, that quantity squared, minus the 1 that I just subtracted. Now I'm going to multiply everything by negative 3 over 1. So now we have y plus 1 is equal to negative 3 times the quantity of x minus 1 squared. And then we have negative 3 times negative 1 is going to be positive 3. All right, so lastly, I just have to subtract 1 from both sides. So we have y equals negative 3 times the quantity of x minus 1 squared plus 2. Now, this was a little bit more of a roundabout way of doing it, but if it makes more sense than your textbook, great. I want you to find whatever way works best for you. So now we actually need to graph it, but I'm just going to do a really quick general graph, and I'm going to have you finish up the XY table, and I'll be checking that in your notes. All right, so according to our vertex form, we have a vertex located at 1, 2. Remember that x coordinate's always the opposite sign. A good way to remember is the fact that we always have the opposite sign when it's a quantity inside of parentheses here. Okay, and I know that it's going to start to open downward, okay, because we have a value of negative 3. Scratch that. I'm going to help you make your XY table. I'm feeling pretty generous right now, so I'm going to give myself some room over here. So we're just actually going to plug in values for x and y into our vertex form. So once again, smack dab in the middle goes my vertex. Values to the left and to the right by 1 unit will share the same y value. So it's actually going to make more sense for me to plug in our x value of 0. So if I plug in 0 here, we have 0 minus 1 is negative 1. Negative 1 squared is positive 1. And negative 3 plus 2 is a y value of negative 1 here. Okay, so I'm going to zoom in. I'm going to plot these values. So 0, I'm at negative 1. And then over here, I'm also at negative 1. So then look at how steep that's getting. And the reason it's getting so steep is because this parabola was vertically stretched because we have an a value of 3. So that's something else that we have to point out. Because I have an a value of 3, I'm vertically stretched by a factor of 3. Vertically stretched by a factor of 3. Another observation, I'm moving to the right by 1 unit, and I moved up by 2 units. Make sure you're writing down your transformations. It is definitely a very important part to know in this learning target. All right, last example. And the last example is actually just for writing an equation given certain piece of information. So it might actually be a review for you depending upon where you took Algebra 2, or Algebra 1, I'm sorry. You're in Algebra 2. So we're writing an equation given our vertex and a coordinate. Now notice that a coordinate is x, y, and a vertex is our value for h and k. And when given the vertex, it's actually going to make the most sense to use the vertex form of our equation to solve for a piece of information. I have an h and a k, and I also have an x and a y. The only thing I don't have is an a. So I'm going to plug in my y value of 1 for my coordinate, and I'm going to plug in my value of 2 for x. Again, these were my coordinates. Now my value for h, we have minus negative 1 squared, and our value for k is positive 4. So now we have, if we subtract 4 from both sides, 1 minus 4 is going to get me negative 3 is equal to a times the quantity of, well, 2 minus negative 1 is actually 3. So we have negative 3 equals, and 3 squared is 9, so it equals 9a. Divide both sides by 9, and we get an a value of negative 1/3. So when we have an a value of negative 1/3, this means our parabola is actually going to get very wide. Okay, it's kind of getting condensed, vertically condensed by a factor of 1/3. So then, writing our final equation, y is equal to a value of negative 1/3. We have x plus 1, we're going to simplify this part here, squared plus 4. And here is our parabola. We know a few observations about it, properties-wise. So we're going to face down. And when we're opening down, it's important to recognize here's your transformation. You essentially flipped. You flipped across the x-axis, so to speak in proper math terms, we reflect across the x-axis, okay? That's because we have a negative a value. Another transformation that you did, you shifted to the left by 1 unit. Left by 1. And lastly, we also did a upward vertical translation. We moved up by 4. And I already verbalized the fact that we were vertically condensed.